Suppose I tell you that the derivative of a function is 2x. And I want you to tell me what is the original function. So what is f of x? Well, we have to ask ourselves, what do we take the derivative of to get to 2x? And what we take the derivative of is x squared. If we take the derivative of x squared, we get 2x. But there's a catch, because if we take the derivative of x squared plus 1, we still get 2x. So the derivative of x squared plus 1 still goes to 2x. So take these arrows to mean the derivative. If we take the derivative of x squared plus 100, that still goes to 2x, because when we take the derivative, that constant goes away. We could do this forever. We could add any constant we wanted. X squared minus pi, when we take the derivative, that still goes to 2x. So what we're going to do instead of doing of trying to pick a constant, because we know there's an infinite amount of constants we could put here, and they're all of these functions are different functions, but when you take the derivative, they all become 2x. So what happens is, instead of trying to choose one of these, we're just going to add an arbitrary constant. So all we're going to say is, okay, plus c, plus some constant. And we know that when we take the derivative, that constant's going to go away, and the derivative will be 2x. Also, notice the constant could be 0. You could be adding 0, in which case we would just have x squared. So what does this mean? Well, this process is the process of taking an antiderivative. We're undoing the derivative. So x squared plus c is the antiderivative of 2x. We undid the derivative. And something interesting happens, that x squared plus c is not just one function, it's an entire family of functions. And what do they look like? Well, they look something like this. X squared plus 0 passes through the origin. So that's one function. That's an antiderivative of 2x. X squared plus 1 passes through y equals 1. So that's another function. That's an antiderivative. X squared plus 2, x squared plus pi, x squared minus 3, so on and so on. All of these are antiderivatives of 2x. So each single one of these is an antiderivative of 2x. All of them together are this family of functions x squared plus c, where c can be any constant. So it's just something interesting to notice. Don't get too caught up on this. But the antiderivative is a family of functions. It's not just one function, it's all of these. A different function for every different constant you add. Okay. So let's just do another example of finding an antiderivative. So let's say g prime of x is equal to cos of x. And so what is the antiderivative of g of x? Or what is the original function? What is the antiderivative of g prime of x? Meaning what's the function that we took the derivative of to get g prime of x? Well, this is just sine of x. When you take the derivative of sine, you get cosine, but we can't forget we got to add this plus c, because there could be any constant there, and when we take the derivative, that constant disappears. We just get cos x. So this process is the process of undoing a derivative, or finding an antiderivative, and there's specific notation we can use. So up here, the notation we would use is the antiderivative, or the indefinite integral, that's a different name for this, of 2x is equal to x squared plus c. X squared plus c. So we can think of this as, this is the integral symbol, and we sandwich the function between the integral and this dx. And so we have the integral of 2x with respect to x is equal to x squared plus c. Or the antiderivative of 2x with respect to x is x squared plus c. So keeping that in mind, how would we write the antiderivative of cos x? Well, the antiderivative of cos x with respect to x is equal to x squared, not x squared plus c, is equal to sine x plus c. So this symbol, you can think of it as saying take the antiderivative of whatever's sandwiched in between the integral symbol and the dx. Take the antiderivative. So maybe let's do another example using this new notation. So what's the antiderivative of e to the x? Well, the derivative of e to the x is just e to the x. So the antiderivative of e to the x is just e to the x plus c. Now the cool thing about antiderivatives is we can always verify them by just checking that the derivative works out. So let me show you what I mean. First, let me erase this. So we could always check this, and you might want to do this on tests if this is brand new to you. We can always check this by taking the derivative of what our antiderivative was. So we're going to take the derivative of x squared plus c. We should definitely get 2x, exactly 2x. And that's exactly what happens. We take the derivative of x squared, that's 2x. We take the derivative of c, that's 0. So this is 2x plus 0. Or in other words, just 2x. We could do that with all of these. Take the derivative of sine x plus c. And this derivative of sine is cosine. The derivative of c is 0, so we're just left with cosine. Exactly what we took the antiderivative of. And the last one here we can verify it's going to work out the exact same. The derivative of e to the x plus c is just e to the x. The derivative of e to the x is e to the x, derivative of c is 0. So there we go. So these antiderivatives are really easy to verify because we know how to take the derivative of anything that comes our way. So if you're ever not sure about what the if you got the antiderivative right, take the derivative of your answer. And you should get, once you take the derivative, you should get whatever is inside the antiderivative. Okay, so we're going to spend a little bit of time learning some techniques for finding antiderivatives. See you in the next video.